Is there any pink in here? The one problem with not picking up your homework is making it glaringly obvious that you're not attending any of the lectures. Just sitting in my... All right, so before we get started, we're going to take a look at a homework problem. And that homework problem is going to be 61?
64.
64. From chapter 2. All right, so first thing, let me make sure that I have it, because I have some supplement homework notes. Let me make sure it's not in there. Okay, it's not. All right. So let's see. All right. So this looks like a messy one, unfortunately. This is one of those where if you see something like this on a quiz or an exam, you just got to kind of keep your cool and take things, one step at a time. And it helps if you can try to combine multiple chunks at once, just because it reduces the number of pictures that you got to draw. But anyway. So to make a long story short, it asks us to find the equivalent resistance between terminals A and B. And so this is a problem where we're going to have to, all right, give me a second to draw this. My hope is that there's going to be some sort of a shortcut here where you can get rid of a whole bunch of things at once. So it looks like it's pretty much the same configuration on all four sides, right? With these two sets of, or these like four resistors in sort of like an H configuration. So if we can figure out how to get an equivalent for those, then we should be able to solve this with relatively not much effort. That's going to be the most important part of this guy. But this is a good example of how to deal with the more complex problems that you might see. Pen's running out of ink, but so it's 12, 10, 14, 8, 8, 8. Nine, 6, 9, 4, 6. 8. Okay. So this is what we're done. Alright. This type of circuit, and my pen's running out, I know on top of this graph paper it's kind of hard to see what's going on. After this I might have to go back to my office and get another pen because I don't know how that's going to work for lecture. But, so, what do we have to do here? Obviously, we got to simplify it, okay? And so the thing that really sticks out to me, what is this, homework? So the thing that really sticks out to me is these foursomes, right? If we can find a way to replace all four of these foursomes with an equivalent resistance, then that drastically reduces the size of the circuit. Now the question is, and I haven't done this problem before, I don't know, can we do that? Well, it seems at least like in part, right? So what do we have here? These two resistors are in parallel. These two are in parallel. Unfortunately, these two sets are not in series because you have that node right there. So we're not going to be able to combine all four together, but we should be able to do combos of two. So what I'm going to do is I'm going to circle in red the main things that we think that we can combine together in one step. Yeah.
So on like the left and right side, right, there's a node in the middle. On the top and bottom, is there node in the middle there? Like
yeah, the picture's not very clear. These two are the same node. These two are the same node, and these two are the same.
Oh, okay.
Yeah.
Okay.
Sorry, I got to use my other pens have a thicker point, so it shows everyone's clearly. Okay, so let's circle the things that we think we can combine right off the bat. Okay, these two are in parallel, so they can be combined. These two are in parallel, so they can be combined. Now this, we have these two in parallel, these two in parallel, and then the two chunks are in series because there's nothing connected to the midpoint here. So we can connect all four of these together. And actually, these two are in series with that, right? So you could actually extend this to go all the way up like that. So we could combine all those together in one chunk. Same thing here, right? Because we have parallel, 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 but they are series, series, series. So we would be able to create one chunk that looked like that. And then I think that's pretty much it. So what are these values going to look like? So just to write out the pseudo math of it real quick, it's going to be 10 in parallel with 10 plus 12 in parallel with 4 plus 8 in parallel with 8, right? And we can call that, I'm going to say that's REQ1. This one down here, this is going to be 8 in parallel with 8 plus 6 in parallel with 4 plus 9 in parallel with 6. And that will be called REQ2. This is simply going to be 12 in parallel with 18. 12 in parallel with 18. And I'm going to call that REQ3. And this will be 10 in parallel with 20. And that will be equal to REQ4. So you can see that by taking a high-level look at this bird's eye view and really analyzing what's in parallel, what's in series, we were able to significantly reduce the complexity of this problem. So the first step, I didn't explicitly write it out yet. Step 1 is going to be to examine the circuit and look for opportunities, is the word I would use, to combine 2 plus resistors at once. Because that's really what we're looking for, and I will get another pen after we're done with the example, because I know this is not showing it. Okay, so let's redraw what we actually, you know, I missed. There's another parallel in here. Right, you see this is actually in parallel with that. This whole red circle is actually in parallel with that right there. Anyway, I think we did a pretty good job of coming up with the parallels. Okay, so now redrawing it. Really, I guess there's no way that I can get both on the screen at the same time. This is as far out as it zooms. Okay. So let me start off by drawing the part that's not simplified. That'll maybe be the easiest. So this is here. Okay. This is the 4 ohm resistor. That's point A. And this is point B. All right, and we have a. Okay. So we have the uncombined (8 ohm) resistor. That's again still from the previous circuit. And we have the uncombined 5. Okay. So now let's fill in what we know. So we have REQ3. We have REQ4. And we have another resistor, which is essentially just in parallel with this one. So I can just draw it like this. And that's REQ1, and that's REQ2. Okay. So does everybody understand how we went from here to here? We combined all 3 of these together into that resistor. We combined these 2 into that, these 2 into that, and then all 3 of these into that. Okay, now we've got to come up with the values. We haven't done that yet, so.
I have values.
Say it again?
I have values.
Okay, awesome. So, step 2, calculate the value. Alright, what about REQ1?
Yes, 12.
12 at 1, 2?
Yes, 1, 2.
Alright, REQ2?
10.
Alright, REQ3?
7.2.
7.2, and REQ4?
6. 6.67. Second two letters.
Got it. Alright, and then now, let's do the circling game again, and you'll see that really what we can do is we can combine everything between this point and this point. Like these three can be combined together, and these three can be combined together, and that'll give us a circuit that we're pretty close to the end at that point.
Are those parallel combinations?
These two are in parallel, and then this is in series. So parallel, parallel, series, parallel, parallel, series. And so the value for this one would be REQ1 in parallel with 8 plus REQ3 would equal what I'm going to call REQ5. And then this one would be REQ2 in parallel with 5 plus REQ4 equals what we're going to define as REQ6. Okay, so now we redraw the circuit. So redraw again. So what we'll be left with is essentially, and what I can do is I'm going to flip the bottom half up to the top, because there's really no need to draw the circuit so we have a bottom half and a top half, right? I can just flip everything up to the top half. So we have point A, we have point B, we have this resistor, okay, and then now essentially all we have is this. Where this is REQ5, and this is REQ6, and this is 4, and this is 8. That's it, right? Because all these became one branch, which is located between those 2 points. All these become one branch, which is located in between the 2 points. And then now you can see that our final grouping will be all of these together in one. And the equation for that would be, and I'll call this REQ final, that will be equal to 4 plus the parallel combo of REQ5 and REQ6 plus 8, right? Because it's this plus those plus that. So step 4 is going to be calculated. So as usual, I need some help. We never calculated what R5 and R6 were, and then we got to do the final. So what's R5 and R6?
12 and 10.
12 and 10. Okay. So this equals 12 ohms. This equals 10 ohms. And then this one. 5.45?
You have to add the 4.
Yeah, you have to add the 4. So it's 5.45 plus, okay. So that means that it's,
17.
yeah, 17. Now let's see if that matches the book has. 17.45. Moment of truth. Yes. Sweet vindication. 17.45. So, I mean, I know the book solutions are not always the best, right? It seems like they just threw out a whole bunch of equations and expected you to kind of understand what they were doing. If you take a look at the equations, it essentially lays out what we did, which was they combined R1 and R2. They started out by doing these, by collapsing in the edges. And then, I mean, they follow the same process we did. They just didn't draw pictures. Okay, so I'll post this. I'm going to add this to the file that's available here. If you go to supplementary homework solutions by hand, whatever, I'll put it right after problem 1.43 in these notes. I'll include W. Sorry, 2.43, W2.64. Yeah. Okay, so everyone hang tight for 1 second. I really do need to go to a different pen or two, or else this is not great. So, you know, actually what I'll do is I'll leave this up here if people want to take a look at it and review it while I go get my food. It shouldn't take me more than like 5 minutes.
It's true.
Yeah.
I'm very tired. I'm not even tired because I didn't get enough sleep. I'm just bored. If I'm not thinking or like doing anything, just like my eyes start shutting.
And just added them in when they were
Combine this one.
It's just so gross out.
I actually like.
I hate
I
when people
hate
say that it's
water.
gross out because water is falling from the
I
sky.
hate water.
It is water. You drink water all the time. You bathe in water. You wash your hands in water. Water is not gross. Okay, you use water to get clean. So stop saying water is gross.
I
Because
don't like water.
Well, I don't know if it's the weather or not. I actually like rainy weather. I don't know if it makes me feel tired.
It's not like our paths are muddy or our paths are dirt paths. Like we have like concrete paths. We're not trekking through mud. I can understand what you're saying. It's dirty when you have to trek through mud.
Whether or not it's like
concrete.
I don't like wet clothing.
Yeah.
Like, I don't know.
I don't like water.
Yeah, it's more likely that it's going to be the case. So.
I'm going canoeing and or kayaking this weekend. I hope it doesn't rain all around. I have a feeling it's going to.
Does he upload the
Yeah, it's not like it matters. I'm probably gonna bring my swimsuit and just like roll out of my kayak anyway.
Yeah, basically just wait until the end.
It's probably gonna be cold though, but like,
Wait, what?
I'll do that.
I guess I understand, but
As long as it's
Boy Scouts.
You're a Adventure Scout?
Oh, yeah.
Yeah, it was so cold because it was the spring.
as long as it goes above like 50, you're good.
No, it's not a big
So we do like a 4-day trip at the end of the school year.
On Friday?
So it was before the big canoe trip, we took like a small one-night canoe trip.
Yeah.
Besides, like very like
See what I can do
Besides
tomorrow,
those-
and then you said you'll be back for the weekend, right?
everybody kept on tipping because they would like wash their hair and it was cold. Like by the time like the sun went down, it was
What about the
cold.
lab for a second?
Oh, nice.
Because it was so like everybody was like soaking wet because they kept tipping. Below 40.
Below 40, now you're,
Is
Yeah,
it?
you're like,
you actually have something to be concerned about.
yeah. Like, I was sitting there, I was just shivering, waiting for like the rest of the news to come out.
What were you wearing?
I was wearing like, because originally,
Yeah.
it's Sunday, but it's like that time of year when like the sun makes it hot, so like.
Yeah, we had days where it would be like 75 sunny in the day and then go down to like 50s, 40s.
Yeah, because it was like March.
Yeah. Just wearing t-shirt shorts. Like cotton t-shirt.
What?
Yeah, that's not good.
No, it's so good. That one I'm hardly gets like sick the next couple
Valid
days.
excuse if you're like,
Yeah, no, he said it was bad.
Forgetting this is so good.
Yeah, take the 40%.
But if you look at the like, the top stuff is all dry.
what?
Bottom stuff is
So like, haven't Starbucks, but it didn't say it was due,
that
so.
Formula One guy, and it was completely like sealed. It was just
Yeah,
somehow
yeah, that was the
got
one I was thinking.
into the middle of the stuff.
I didn't finish it, but I think most people did.
But the stuff at the top was dry.
It's weird.
Oh yeah, I did finish it.
To this day, we don't know how to.
Oh
The bag
yeah.
is like.
That was like at the very last second though. I remember.
Is it like one of those waterproof ones where you like roll the thing down and flip it?
I don't think it was one of those. It was just like. It was something like that.
Wait, really? He wouldn't give it to us the day before. Wait, what? Oh, that's probably just trying to get back.
Oh, yeah, no, I'm not gonna speak to you. Yeah, I'm not gonna speak to you.
And I brought it home.
Yeah.
And it legit, it worked. We had the rain flies on, and it was coming through the rain. That's how hard it was. And we were just like sleeping in tunnels. So this is just not fun. Summer got to the point where we all went in their cars.
Jeez.
I remember
I felt like clear.
one of my most early like high school trips. It was like
Have you restarted your computer?
absolutely, it was like dinner time, but it was like downpouring and thunderstorming, and like nobody, everyone was in their tents because nobody wanted to come outside and make dinner. We had like hamburger helpers, like we were 2 people that ate. Everyone else was hiding out there.
Is it still slow or is it fun now?
But it's fine.
It must have been like.
As long as it's like warm, getting wet is like no problem. It's not freeze.
Yeah.
All right, so let's pick up where we left off last time. Unless there's any other homework problems, this was good. I think it's always valuable to have us do homework problems in front of the class, because you never know. It seems like when one person brings up an issue with a problem, there's another 10 or 5 that wanted to see it but didn't think that. So where did we leave off last time? We were discussing nodal analysis. So nodal analysis, right, is this formalized way of solving the same circuits that we had talked about in Chapter 2. The main difference was that in Chapter 2, right, we made it our objective to simplify the circuit down to either a single node pair or a single loop or some sort of a voltage or a current divider, one that we had an equation that we knew we could solve, and then get the answer for some fundamental value, whether that's a loop current or the voltage between the node pair, the pair of nodes, and then expand it back out. And that would allow us to get all the values that we need. The problem is that, you know, especially for, let's say, a circuit like the one we just did the homework problem on, imagine if you stuck a source right in between the nodes A and B. Solving a circuit like that using the techniques in Chapter 2 would be not very fun. Okay. Nodal analysis is a more formalized way of looking at these problems, where you don't have to simplify anything. All you have to do is essentially set up the equations in the appropriate way. For nodal analysis, we're going to be predominantly relying on KCL, as well as Ohm's law. Set these equations up, move terms around in the right way. What we saw last time was, essentially you want to have current sources on one side of the equation, then equals the node voltages times whatever their coefficient. So you want to group all the terms by the node voltages. And then once you have that, you can put the thing into a matrix form where you have two vectors in one matrix, right? You have your currents, which should be known. These are the currents being injected into the node. I1, I2, I3, I4 going down. Then you have your admittance matrix. And this contains values that are based on the resistances of the branches. And if you remember, we learned rules. There was an inspection method, rules to automatically generate this Y matrix without having to go through and write all the equations. And then over here, we have the voltages, V1, V2, etc. And this is what we're trying to solve for. So we take this and multiply it by the inverse of that, and then hopefully it gives us all the right voltages. There's a lot of checks that you can use to make sure that you're doing the nodal analysis right before you even get started. One of them is the size. So if I have a circuit and I count out the nodes, there's 5 electrically independent nodes. What should be the size of that? Yes. 4 by 4, exactly. If we have 5 nodes, we're going to consider one of our nodes to be the reference because we need to refer, right, voltage is a differential measurement. So we need to have it be V1 minus V5, V2 minus V5. The absolute voltage doesn't make any sense. It needs a referential point. So we take the 5 voltages, or the 5 nodes, we get rid of one of them, and then we're left with 4. And so we're solving for 4 different values, which means we'll have a 4 by 4 admittance matrix. So that's one main thing to keep in mind. Because if you start off with matrices and vectors that are the wrong size, then that's just already going to lead you down a path where obviously there's no right way to do it, but you're going to start like, I don't want to say bending rules, but trying to make things fit. It's like trying to make a square peg fit into a round hole. It's like you may think that you're making it work, but that's not working. Okay, and then once we have it set up in that form, right, we can solve. Last time, we only talked about, I think, 1 or 2 cases. Because what we saw was that the way that we treat this depends on the stuff that's in the circuit. The form that we have written right here assumes, so what goes in this vector? Only current sources, right? It's the current sources that are connected to the nodes. There's no place in this makeup right here, in this structure, for voltage sources. Okay? Although we discussed a little bit what we would do with those last time. There's also no place in this structure for dependent current sources. Right? Because, let's say one of the dependent current sources is beta times V2. You can't stick that over here. Right? Because you won't be able to solve. The whole goal is that the only unknowns should be in this vector right here. This should be all known, this should be all known, and then you can go and you can solve. So the base case for this type of problem is only independent current sources. That's when you can use the inspection method we talked about last time, and that is one of the easier cases to solve. Did we do an example last time with a dependent current source? Yeah, we did. Yes, yes. So the dependent current source, what we saw for that one, we can't use inspection. So what we have to do is we have to treat the dependent expression, the dependent current source expression, we have to treat it like another KCL, okay? And so we plug that into the equations, and we still use the same sort of technique trying to get the matrix into this one. All right, so. So we did the problem with the beta I23, is that what it is?
Mhm.
Okay. Yeah. Okay, so now the topic that we touched just a little bit upon last time. What day's today, by the way?
29.
Dinner? So we talked about this last time. We said that that nodal analysis actually can often become easier when we have an independent voltage source involved. And there's two different reasons for that. The best case scenario is that if we have a voltage source in between a node and the reference node, then automatically that gets rid of one thing you have to solve for, right? That you were trying to, let's say, V2. Okay, you have a voltage source at V2. Now you don't have to solve for V2 anymore. So you can eliminate that row and that column of the admittance matrix and just solve whatever's left over. So, okay, so let's take a look at example 3.5. And we got a circuit looks like this. I don't think I left myself enough room to really draw this right. So this is 12 volts, this is 6 volts, and there's another resistor up here, but I think that on the state, so. Okay, 12K, 12K, and 9K. All right, so how are we going to solve this thing?
We have a value for that resistance.
Oh yeah, we do. 6. So, first thing we're going to do here, and now we've kind of migrated away from what we were doing in previous chapters and giving all the individual voltages and currents names. Now, what we're doing for the most part is just giving the nodes numbers, and then we can just say like voltage like 2, 3, voltage, current 1, 2, and that pretty much describes it. So, all right. Now, 9 out of 10 times we tend to use the bottom of the circuit as the reference. Sort of usually the way they're drawn, that's a point where a lot of the nodes, a lot of the branches are adjacent to. So we'll go ahead and keep that. So this is going to be the last node. So we have 1, we have 2, we have 3. And we have our reference node. The other reason why it's advantageous to pick this as the reference node So it's advantageous to choose this as the reference node because 2 of the voltage sources connect to it. Right? And we know that anytime we have a voltage source, independent voltage source between a node and the reference node, we're going to lose something we have to solve for. So that's good. Okay, so determine the number of nodes and label them. Step 2 is going to be to determine the desired solution. So in other words, we normally have this V array, which is equal to some unknowns. All right. Normally, this is size n minus 1, or length n minus 1. But in this case, how many values are we going to be solving for? So let's take one step back. Ignoring the independent voltage sources, how many values would we be solving for? N minus 1, right? What's our n for this one? 4. So we'd be solving for 3. So normally, we'd be solving for this. V1, V2, V3. But we know some of these values. Okay, we know that V3 equals negative 6 volts. And we know that V1 is equal to 12 volts. So that means we're left over with lowly old V2. That's it.
And where is V2? What is it? Oh, it's just, so these voltages are just the voltages through the nodes.
The voltage, if you want to write it in a more, and I'll just write a note down here. Note, V2 is equal to V24. The voltage between 2 and 4. Like this is V2. It's assumed that the notation, we got rid of the second, because they're all referred before, we just dropped the second indice, so index. And so, yeah, V2 equals V24 equals what you could call V2 reference. All of them would be the same. All right, so we just got to solve for 1. That's nice. So step number 3. We gotta set up KCL for this node. So what is that gonna look like? It's gonna look like I 1, 2 plus I 4, 2 plus I 3, 2 equals 0. And that's just, I mean, a no-brainer, right? This is I 1, 2, this is I 4, 2, this is I 3, 2, which is all the currents going in. And then now we gotta substitute. So we can use good old Ohm's law to substitute. And so what that'll leave us with is I 1, 2 will be equal to, as the picture shows, V1 minus V2 over 12,000. I 4, 2 will be V4 minus V2 over 6,000. And then I 3, 2 will be V3 minus V2 over 12,000. Okay, the only unknown that there is in this equation is V2. So that's the only unknown. The rest of it is known. So what we can do is separate out the known and the unknown. And what we'll end up with is an equation that looks like this. So we'll have on one side V1 over 12k plus V4 over 6k plus V3 over 12k equals, and then on the other side it'll be 1 over 12k plus 1 over 6k plus 1 over 12k times V2. That's just rearranging those terms. This, sorry?
And it's all positive
Because I move it to the other side, yeah. This is equal to 0, because V4 is 0. This is 12 volts, and this is negative 6 volts. So, right, this is really just a calculator problem now. So you'll have, this will be 12 over 12,000 will be 1 milliamp. So you'll have 1 milliamp plus 0 minus 0.5 milliamps over 1 over 12k plus 1 over 6k plus 1 over 12k, and that'll give us our V2. Anybody can plug that in? Say it, say again? So, that's that. A good example of what to do when you have a node in between the reference and another node only. Okay, now the next question we have to ask is, okay, what if we have an independent voltage source between two non-reference nodes? And so what I'm going to do is I'm going to draw part of a circuit here. Okay. So normally what we would do is we would consider these two nodes separately in our analysis, right? But as you remember, KCL applies to groups of nodes as well as a single node. Okay, it's all conservation of matter, conservation of charge, depending on how you want to look at it, right? Regardless of how big the bucket is, whether it's a node or it's a group of nodes, whatever goes into it has to come out. So the one thing that you note about this, and I'm going to call this node A, and I'm going to call this node B. You know, right, that if we apply KVL here, we end up with, and I'm going to call this, so this is VA to ground and VB is to the reference. Just for to make the discussion easier. You know that VA plus whatever this VS is equals VB. So VB equals VA plus VS. Which means that we don't need to solve for both of these nodes as part of our nodal analysis. The answer is going to be redundant because once we know one, we already know the other. So what we can do is define this okay. So what we can do is we can define this as a supernode and solve it as one element in the analysis. All right. And then at the end, when we get the answer, whether we solve for VA or VB, we're going to solve for one of those two. Okay. You can get the other one by simply just putting them together. So still, well, we'll get there. All right, so let's take a look at an example. Does anybody have any questions about the supernode? So how many currents would there be considered or would be present in the KCL expression for the supernode? Well, but you have to remember, KCL is looking at all the currents going into it. So you're looking at external, not the internal. So there's this current, that current, that current. There's 4 currents that need to sum to 0 inside to make KCL applicable to this supernova. All right. So we're looking at nodal analysis for supernode and the circuit that we're dealing with. Looks like this. All right, that's it. So, first step. How many nodes? Label. So the first instinct is going to be to, well, we can go ahead and label them. We'll have node 1, we'll have node 2, we'll have node 3. Okay, so there's 3 nodes. But we could also represent it as we could also represent it as 2 nodes with 1 node being the supernode. Okay, and so that's the method that we are going to we're going to use. So we're going to say for our purposes, n equals 2. Okay, not 3 as it would be otherwise. And so what we'll do is, I'll call this node, I'll give it a name. So this is going to be called node X. All right. So let's write out KCL for this node. All right. So the first thing we have is we know, right, that there is this current entering the supernode. So we have 6 milliamps. We know also we have 4 milliamps leaving the supernode, so that's minus 4 milliamps. So those are the sources. Then we can also define a current we're going to call V or I31, and another current which will be called I32 equals 0. Right, where this is I31. So if you note, right, nodes 2 and 3 are not gonna, that should be 1 and 2, are not gonna disappear completely from the analysis. They're still there. It's just that they're not considered the node that we're solving for. This will all work out though, so it's easy. Okay, so let's continue down our regular path. And let's substitute for Ohm's law. And so what that'll leave us with is, and I'm going to start moving things to opposite sides. So we'll have 2 milliamps plus V3 minus V1 over 6,000 plus V3 minus V2 over 12,000 equals 0. Obviously these are going to go away because they're 0, they're the reference nodes. But what problem do we see? What's the problem with this picture that we have right now? V1 and V2 are still in there. We have one equation, and we have two things that we want to solve for. Okay, so that's not good. How can we do this? Step 4. Use supernode definition to simplify. And so what that means is we'll have 2 milliamps, and I'm going to move the other stuff to the other side. So this will be 1 over 6,000 times. And so our definition all the way up here, which we didn't explicitly write it out, but I'll put it up here. So supernode definition is essentially that V1 equals V2 plus 6 volts. And that's just taken directly from good old KVL. Okay? You take KVL for this loop right here, you'll see that the V2 plus 6 volts gives us V1. Can you all see that? All right, and so now we can take that and we can substitute him all the way down in here. So now we're going to take that value of V1, substitute him in down there, and what that means is instead of having V1, we'll have V2 plus 6 volts. And then I'll have plus 1 over 12,000 times V2. And so now our problem is fixed. We have only one volt that we have to solve for. All right. So step 5. Arrange terms and solve. So all we gotta do is isolate V2. We know that 2 milliamps, and then we'll move that other term to the other side, minus 6 volts over 6,000 ohms will be equal to 1 over 6,000 plus 1 over 12,000 times V2. And then we know lastly that V2 will be equal to 1 over 6,000 plus 1 over 12,000 times 2 milliamps minus 6 volts over 6,000. So now we just got to put that into the calculator. Anybody do that for me?
So that's in terms of seeing 6,000, 12,000. Right? 1 over 1 over 50.
No, because they would have to have the same denominator. Yeah. I mean, I guess you could do it in your head because it would be 2 over 12,000 plus 1 over 12,000. So 12,000 divided by 3, right?
Yes.
So 4,000, and then just go ahead and, well, so this right here is 4,000. What's this?
0.001.
And then so we end up with 4.
Yeah.
That's our answer. So, I mean, as you can see, doing a problem with a supernode is not, I don't think it's harder. I don't think it necessarily makes it that much easier as compared to like when you have the voltage in between the reference denominator. It's sort of like a wash. You have one less equation that you have to deal with, but then you have to stick the supernode definition. What ends up happening is, if you look at this from a strictly mathematical point of view, you're eliminating one of the KCL expressions and substituting this expression in its place. So it's, and all of these are just, when you get rid of the name mesh analysis, nodal analysis, it's just the linear algebraic description of the system. You know, and in order to have that be, you know, solvable, you need to have the same number of equations as you do variables. So you're substituting this for the other KCL expression. All right, what's next? All right, the next example is a long one because it's the last of the 4 types that we're going to talk about. We've done independent current sources, we've done dependent current sources, we've done independent voltage sources, both, you know, supernode and non-supernode, and the last is going to be dependent voltage sources. So that one is, the example takes a little bit of time to go through. And I'm not a big fan of starting examples, so we'll do it next time. So I'm going to stop there with new material. Are there any questions that I can field for the quiz that's coming up on Monday? Yes?
Is it just chapter 2?
It's just chapter 2. Everything's cumulative, but there wasn't much in chapter 1 really to have it show up. So you should expect to see a problem very similar to one of the homework problems. Independent voltage source, dependent current source, couple of resistors, one that you can solve down, you can pare down using parallel and series combinations, come up with the answer, and then expand it back out. Make sure to remember about that delta to y connection thing. Again, that's going to be in your cheat sheet, the equation, but you have to remember how to use it. It's very specific. You have to remember how it's kind of like cutting a hole in a piece of paper, yanking it out, and putting it right back in the exact same way. If you rotate something or accidentally leave out a resistor or an element, then that can throw you for a loop. There's not going to be a very
if there is any sort of theoretical like question, like a word answer question, it's going to be very short. It's going to be predominantly a mathematical problem that you have to work out and get like a minute.
How long do you tend to take?
I usually give half the class. But that being said, someone who really knows it, it takes 7 minutes to complete, I would say. Like if you gave me, I mean obviously, I have the benefit of doing this for 7 years, but if you gave it to me with just pencil and paper, I would say, yeah, that's 6 minutes. So 45 minutes is like a nice buffer for, you think about what the homework problems you've done, take a look at the cheat sheet and all that type of stuff. Yes.
Will you be emailing a copy of the cheat sheet?
Yes. I need someone to remind me. Just someone in class remind me. Because I will do it when I get back to my office, but then I always forget. So when I'm in front of my computer, if someone emails me, then it just prompts me to do it right then and there. Okay? But I will try to remember when I get back to the office. Well, this is 4,000 times